Bismillah ar-Rahman ar-Rahim. Today we will start our discussion on the uncertainty, and this chapter refers to the textbook of AI that is by Russell and Novick. And in this book, we'll try to cover the concept of uncertainty, probability, syntax, and semantics, how to represent that probability, how we can infer, and what is the application of Bayes rule. So we start with our concept with the understanding of the uncertainty principle. How you can define an uncertainty? Let's suppose if you say that there is an action AT is equal to leave for airport T minutes before flight departure. Will AIT get me there on time? So again, there is in this question you can see yourself that there is no certainty. There are possibilities. Either I can reach there on time, or either I can reach well before the time, either I can reach after the time. So there is uncertainty. And obviously, in real life problems, most of the time we deal with uncertainty. For example, you invest some money in a stock exchange and you want to know how you can earn the profits. So obviously, there is an element of uncertainty. There are certain factors by which that stock market varies. So, so, um, it means that again we have to tackle that uncertainty in our model. Take other examples as well. For example, take the example of driving. So you drive on the car and you take various actions on the road. Sometime you accelerate, sometime you stop, sometime you slow down, sometime you overtake. So all those your actions, obviously, whenever you take these actions, in given situation or in the given environment, there is an element of uncertainty. So that is the next example we have, and there are so many other examples you can see. Let's suppose we are talking about a game scenario. So in a game scenario, let's suppose take example of a football. A football player moves on and try to kick the ball such that the ball goes into the goal. But there is a chance whether it will be intercepted or it will not go into the goal, just misses the goal, hit the bar, or stopped by the goalkeeper. So there is an element of uncertainty. Or for example, in real life, let's suppose if you're talking about monitoring applications or any other kinds of application, there is an element of uncertainty. So why that uncertainty problems do occur? So you can see number one scenario is about partial observability. Because this is because of partial observability. So we deal with various kinds of environment. We do not only deal with the environment where we have full observation or full observability. There are problems where we have full observability as well. For example, playing a chess. So it is a fully observable environment. But even then, that is difficult to traverse in the chess as well. But partial observability, good example of partial observability is on the road. So when you are on the road, there are other agents as well on the road. There are other vehicles as well. There are pedestrians. So you cannot observe the whole environment at once when you are taking those actions. So that is one of the factor that where you have the element of uncertainty. Similarly, you can apply this in investment case, which I have discussed earlier on, or even you can apply it in a football game. There is also a partial observability. Number two, there may be some noisy sensors. So how you take the input. So it means whatever the input you have, input itself is noisy. It means it is not clear, incomplete maybe. So again, if this is the case, then you have to take the decision. So you will rely on the information which is available to you. Uncertainty in action outcomes. Yes, there is. It is related with the action outcomes. Uh, let's suppose we're talking about a problem earlier on, or we'll define a problem in the next slide as well. Let's suppose you want to build a system where you can replace your flat tires. So when you are on the road, you want to know when your tire is flat and how to change that tire. So uncertainty is there. You may be on the road, and on the road you might don't have a fuel, and there is no pump which is near to you. Let's suppose you have a flat tire and you don't have any puncture shop which is there, and let's suppose you don't have stepney as well. So there is an uncertainty. So while we are dealing with such problems, we have to consider the action outcomes. And obviously, those are the possibilities. We have to see how those possibilities can occur. Immense complexity of modeling and predicting traffic. So in case of road networks, let's suppose there is a complexity because there are so many agents which are on the road as well. And we have a mixed sort of traffic patterns over the 24 hours on the road. Many events occur. Let's suppose there are rallies on the road, there are school timings, there are office timings, in the night, near the restaurants. We have various kinds of traffic patterns. And whenever there is a bottleneck, obviously that creates the trouble overall, the network. So modeling such a situation is a complex task. It's not that simple to model the situation. Hence, a purely logical approach is required. And in the purely logical approach, either you go for risk falsehood. We have to have the risk falsehood. For example, A25 will get me there on time. That is the action. So that action is that 25 minutes will get there on time. So what is the risk falsehood? Or leads to conclusions that are too weak for decision making, or you led to those conclusions which are so weak. For example, A25 will get me there on time if there is no accident on the bridge and it does not rain and my tires remain intact, etc., etc., etc. So then obviously in that scenario, the decision making of course is difficult. The conclusions are not perfect. So these are the problems we might have. Okay, making conclusions under uncertainty. There we need to have a belief. Suppose that I believe the following. Let's suppose the probability that A25 gets me there on time, given this, whatever the reasons we have, is 0.04. Let's suppose probability of A90 is 0.70, probability of A120 is 0.95, and probability of 1440 is 0.99. So the straightforward question is that how you will opt, which situation you will opt, or which action you will opt. So obviously you will opt for the action where you have the highest value of the probability. So that depends on my preferences for missing the flight versus sleeping at the airport. So it's up to you. Either you can reach early. It is the preference that you do not want to miss the flight, so you want to be early there. So you might sleep over there. That is your preference. Or you want to get on time. Or you are not supposed to in a hurry. You might have an extra flight book tomorrow morning. So you are not in a hurry. So utility theory is used to represent and infer preferences. So whenever we have such preferences, then it is better to apply the utility theory concept. when we talked about various types of agents, we talked about the simple reflex agent, the goal-based agent, the model-based agent, and we also talked about utility-based agent, which is based on the concept of the utility theory. So why? Because you have various preferences. So you might go for a mathematical function which returns you a utility value, that which is a quantifiable value. And on the base of that quantifiable value, you will decide about yourself the state of happiness, in which state you want to be happy, to be there, or which preference to be followed first. So if you have many preferences, then you have to apply that utility theory as well. So decision theory itself is based on both the concepts, not only the probability, but it also depends upon the utility, because the probability is there, but of course that probability is related with various preferences. So when we combine these two things, so we can say a decision theory is the utility theory plus the probability theory. So here some probability basics, and I can realize that you people already have that knowledge. Just for your revision, we begin with the set sigma, the sample space. Let's suppose we're talking about a die. So there are 6 possible rows of a die. So that is our sigma in that case. So W belongs to sigma is the sample point, possible worlds, atomic event. What is a possible world scenario? Possible world means what? Let's suppose if I ask you to toss a coin. So if you toss a coin, there are 2 possibilities. One is head, the other one is tail. So you can say me, sir, there are 2 possible worlds. Either it is a head or a tail. And if I asked you to toss 2 coins together, what are the possible worlds? Then you will reply to me that there are 4 possible worlds. Both can be head. One is head, the other one is tail. First one is tail, the other one is head, or both are tail. So there are 4 possible worlds. So we have to see how many possible worlds we are dealing with. That basically makes our sample space. A probability space or a probability model is what? Is a sample space with an assignment PW for every W belongs to sigma. So sigma itself is infinite. So it includes all the possibilities, whatever the possibilities we have. But we want to have the assignment. So that assignment is what? That is PW, and where W belongs to sigma, such that the important thing is the probability always between 0 and 1. If you say me that the probability is 1.1, so this is rubbish, because probability cannot be 1.1. The probability cannot be minus 0.1. Not possible. Probability is always between 0 and 1. So either you talk in terms of the values lie between 0 and 1, or you talk in terms of the percentage. Let's say you say that there is a 60% probability that, or a chance that he will catch the bus or he will catch the train. So that it means that you're talking about probability of 0.6. So probability always between 0 and 1. The second principle regarding probability, which is very, you can say, fundamental principle, that sum of all probabilities is always 1. So if you combine all those probabilities together, the value should be 1. So P1 is equal to P2. What it says? It says that the probability for the... So in this case, the probability, we're talking about a roll of a die. So there are 6 possibilities. Either it can be 1, 2, 3, 4, or 5, or 6. So chance is equal. So either you want to calculate the probability of having 1, so it means 1 upon 6. Probability of having 2 is 1 upon 6. So if you add all these probabilities together, it will be 1. So an event A is a subset of sigma, where PA is what? Is the sigma summation W belongs to A PW with probability of a die roll less than equal to 4, less than 4. So less than 4, there are only 3 possibilities, P1, P2, and P3. So that is equivalent to 1 upon 2. So it means that you can say with a confidence that there is a 50% chance that whenever you roll a die, it will be either 1, 2, or 3. Concept of a random variable. A random variable is what? Is a function from sample points to some range. That is example, that is odd one is equal to true, has a Boolean value ranged because it is either false or true. So that random variable can take two values. That is why it is called Boolean ranged, but not necessarily that all random variables are Boolean value ranged. So we may have a multi-valued random variable. So P induces a probability distribution for any random variable X. So that random variable X, if you define in the probability distribution, you can say that Px is equal to Xi. It can take various value of X. It's obviously the sum of all W's, XW is equal to Xi, PW. So when you say P odd is equal to true, then there are three possibilities. Either it can be one, that random variable can take three values. Either it can be 1, 3, or 5. So that is the probability of 1, the probability of 3, and probability of 5. Again, if you sum up all these three values, you can get 1 upon 2.5. So there is 0.5 probability that the value takes these odd number of values. So given a Boolean random variable A and B, you can say that event A is set of sample points where AW is equal to true, and event not of A is equal to set of sample point where AW is false. And event A and B is equal to points where AW is true and BW is true. So if both are true, only then that will be true. So often in AI application, the sample points are defined by the values of a set of random variable. That is, the sample space is what is the Cartesian product of the ranges of the variable. So let's suppose if one variable is a Boolean variable and the other variable takes three values. So if you make a Cartesian product that is 2 multiplied by 3, so it means you have a 6 pair of sets. Okay, so you have a 6 pair of sets. For example, if I ask you to toss a coin and roll a die, you can do the same thing together. So tossing a coin either gives you head and tail, and rolling a die either gives you 1 to 6. So how many possibilities you might have? So 2 multiplied by 6, so there are 12 possibilities. Either we have a head or 1, either we have a head or 2, head or 3. Similarly, we have tail or 1, tail or 2, tail or 3. So we have 12 number of possible values which are defined. So proposition is equal to what? Is a disjunction of atomic events in which it is true. Okay, so what are my propositions? The propositions are disjunctions. You can, whenever I say disjunctions, it means it are separated by or of atomic events, separate events, which is not further decomposable, in which it is true. For example, A or B equivalent to. Uh, three lines represents a symbol which is normally called as equivalent to whenever we are equating the logical terms, or where there we use equivalent to. So A or B is equivalent to not of B, not of A or and B, or A and not of B, or A and B. This implies that probability of A or B is equal to probability of not of A and B plus probability of A and not of B plus probability of A and B. And you can confirm it by making a table, and you can verify it that the values of uh, these various atomic events. So definitions imply that certain logically related events must have related probabilities. So here you can see in terms of a Venn diagram. So let's suppose we have A and we have B. So there is some commonality which exists between A and B, and that commonality right now is represented, let's suppose, in terms of A and B. So let's suppose if you want to calculate the probability of A or B, so it means it includes the probability of A plus probability of B, and you will obviously minus the common elements, the probability of the common elements of A and B. So an agent who bets according to probabilities that violate these axioms can be forced to bet so as to lose money regardless of outcome. So obviously, if you do not follow these rules and you go for a bet, it means you are a fool. So because not only you are, it means you are not interested in the outcome. You are just there to lose money. So we have to think about the problems we are dealing with, and then we can compute all those possibilities. We can also compute the probabilities and the uncertainty which is there, and that uncertainty, that probability values, that uncertainty help us to make those decisions in the right way. So it is up to you how we can represent the knowledge, how we can use that knowledge. Syntax for propositions. So how you define various propositions, it is important. Propositions or Boolean random variable. Let's suppose take an example of cavity. Uh, we all have cavities. Sometimes these cavities developed in the early age, in the middle age, or in the late age as well. So cavity, do we have a cavity? So that represents a cavity. So if that cavity is true, is a proposition also written written cavity. Discrete random variables, it can be either finite or infinite. For example, weather. Let's take weather as a discrete random variable, which can take some discrete values such as sunny, rainy, cloudy, or snowy. So we are the four possibilities we have. So you can say that weather is equal to rain is what? Is a proposition. Now we have to see whether it is true or not in the given situation. But when we talk about discrete random variables, you have to know, or you must know, that the values must be exhaustive. It means that these are countable, not infinite. So obviously, when you are dealing with discrete values, it means they are exhaustive, and not only exhaustive, but also mutually exclusive. So here you can see these values are mutually exclusive as well. And the third thing which we might define in terms of syntax for the given propositions is the continuous random variable. So when we talk about a continuous random variable, it can be bounded or unbounded. Okay, so we have the starting value and we might do not have the end values. So either it is bounded, let's suppose the values between 10 and 20 or between 2 and 3. So it means those are bounded, and it is also possible that these are unbounded. For example, temperature is equal to 21.6. So let's say temperature is a random variable, and that takes the value 21.6 Celsius, and temperature is less than 22, or propositions. So various propositions can be formed, okay, because that temperature values can take uh, um, values between any two given points. So these are not discrete values. So that is treated as continuous random variable. Now the concept of prior probability. There are concept of there is a concept of prior probability as well, and there is a concept of posterior probability. Here we are talking about prior probability. So prior probabilities are also called as unconditional probabilities of propositions. There is no condition associated with this. Okay, if this is true, why this is true? It is just given. This is unconditional. That the probability, let's suppose here, of cavity is equal to true. That is that the value is 0.1. Or we say that the weather is sunny the probability is 0.72. Let's suppose there is a cricket match today and we have a forecast that there is let's suppose there is a 72% chance that the weather will be sunny. So that might help me to take the decision what to do if I won the toss. So, or if let's suppose weather is cloudy, what to do. So these values are totally unconditional. There is no dependence on each other. That is why we call it unconditional probabilities. Correspond to belief prior to arrival of new evidence. So that is the belief we have. Up to what? Up to, it means prior to arrival of any new evidence. Let's suppose the evidence is changed. Now we have the new evidence. So if we have the new evidence, then the prior probability might change. So probability distribution gives values for all possible assignments. Yes. For that purpose, we need to have a probability distribution that tells us that how those values are distributed. In the previous courses, you have gone through with various probability distribution functions, and you see that how in various probability distributions, how that these values are taken by those random variables. You talked about, you studied the normal distribution, Poisson distribution, binomial distribution, so on and so forth. So probability of weather is, let's suppose here we have the values 0.72, 0.1, 0.08, 0.1. So these are the four values we have, and we have the four possibilities. That is, which we have discussed in the previous slide, that is sunny, rainy, cloudy, and snowy. So that is normalized, that is sum to 1. If you add all these probabilities together, that will give you 1, exactly 1. So joint probability distributions for a set of random variables gives the probability of any atomic event on those random variables, that is every sample point. For example, now you want to develop a joint probability distribution function based on weather and cavity. So we have four values there in the weather, and there are two possibilities because we're talking about either true or false. So there we have only two values. So it means that if I want to combine these two together, I have a 4 by 2 matrix of values. And that matrix is represented here. On the vertical side, you can see it is sunny, rainy, cloudy, and snowy. And here on the left-hand side, in rows, you can see the cavity is true and cavity is false. Even every question about a domain can be answered by the joint distribution because every event is actually is a sum of sample points. So whatever the query related to it can be answered, that okay, this possibility is there. Okay, so if we are talking about the matrix here about weather and cavity, you can have values. For example, when cavity is true and there is talking about a sunny, so it means that will be 0.144. The case of rainy, it can be 0.02. Similarly, it can be 0.016 for case of cloudy, so on and so forth. So this is the concept of prior probability, which is unconditional. Now, when we talk about conditional probabilities, as I told you earlier, that is called posterior probabilities. And posterior probabilities are actually the conditional probability. And how you actually say explain the posterior probability, it means the probability of cavity given tooth H is equal to 0.8. This means the probability of cavity is 0.8 given that the tooth H is all I know. So it means if you know the probability of occurring of one event and then you want to determine the other event, then you use the conditional probability or you use the posterior probability. It does not mean if tooth H, then 80% chance of cavity. No, this is not what we can interpret out of it. So what we interpret here, that the probability of cavity is 0.8 given that the tooth value which is given to us. So it means it's a posterior probability. So normally it is represented as P, and then you have the cavity given the tooth is a two element of vectors of two element vector. So two element vector of two element vector. If we know more, example cavity is also given, then we have the probability of cavity given tooth comma cavity is equal to 1. Let's suppose if cavity is also there, how much cavity is there, then you can compute that value, that will be equal to 1. New evidence may be irrelevant, allowing simplification. In when we were talking about unconditional probability, whenever you have the new evidence, that probability might change. So new evidence may be irrelevant, allowing simplification. Example, probability of cavity given tooth or let's suppose we talk about 49ers win, or is equal to probability of cavity given tooth is equal to 0.28. So let's suppose if talk about any new evidence, it is not relevant to it, it is not related to it. So we determine the same value. This kind of inference sanctioned, sanctioned by domain knowledge is crucial, because if you want to develop your learning mechanism or you want to develop your own knowledge base based on that principle, so you need to have the domain knowledge. Without domain knowledge, you cannot build such system, because it is very important to know how the relationship exists among various random variables in the given domain. So definition of conditional probability, if you move on further, you can say that the probability of A given B is equal to probability of A and B divided by the probability of B. In this way, you can compute the conditional probability. The product rule, which is also important here, gives an alternative formulation as well. That is, probability of A and B is equal to probability of A given B multiplied by probability of B, or probability of B given A multiplied by probability of A. So if you use this product rule, you can say probability of weather comma cavity is equal to probability of weather given cavity multiplied by probability of cavity. So this is the way in which we can define the same assertion. So view as 4 into 2 set of questions, not the matrix multiplication. And if you apply the same concept into more than one variables, then you can define it as a chain rule. So the chain rule is actually what? It's derived by successive application of the product rule. So you obtain this value, and how you obtain this value, you again turn out to the next product, and so on and so forth. So here you can see the probability of x1 dot 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 xn is equal to probability of x1 to xn minus 1, and the probability of xn given x1 to xn minus 1. So that is what that determines the train rule. And by simplifying it, you can have the consolidated value in terms of a product. You can see pi I is equal to 1 to n, pxi given xi, given xi, probability of xi given x1 dot 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 xi minus 1. So by this product rule, we can also formulate that chain rule. So let's see the probability in terms of inference by enumeration. Let's suppose we enumerate and we infer. So we can say that start with the joint distribution. So there are two possibilities here. Either we have a cavity or not of cavity. And let's suppose we have a tooth and not of tooth. And let's introduce a new concept of catch. So tooth with catch, with not of catch, not of tooth with catch and not of catch, cavity and not of cavity. You can see various values. For any proposition, null values or null set, sum the atomic events where it is true. तो जहाँ पे भी atomic, wherever you have the atomic events true, you can sum it. So P of null set is equal to sigma W, where W entails null set PW, wherever these values are true. So you can have this joint distribution by using inference by enumeration. You can see over here these values in the green box. Similarly, you can see here the values, how that these values are calculated, that is P cavity or tooth age. So P cavity or tooth age, you can see you have to add 6 values. If you only want to calculate the probability of tooth age, you can add these values together. That will give you 0.2. Probability of cavity or tooth age, you can have these values. And let's suppose if you want to conditional probability, that probability of not of cavity, no cavity given tooth age is equal to probability of no cavity and tooth age divided by probability of tooth age. So that is the probability of not of cavity and tooth age here is 0.16 plus 0.064 divided by the probability of tooth age, that gives you the value 0.4. So you have that value of probability with no cavity given the tooth age. That is the concept of normalization. The denominator 1 upon p tooth age can be viewed as a normalization constant, that is alpha. For example, P cavity given tooth age is alpha P cavity comma tooth age. So where here alpha is actually what is a normalization constant. So you can take the alpha outside and then you have all the probabilities, probability of cavity, tooth age, and catch plus probability of cavity, tooth age and not of catch. And here you can calculate the values and that alpha lies between 0.6 and 0.4. So inference by enumeration. So how we can infer by enumeration. So let X be all the variables. Typically we want the posterior joint distribution of the query variable Y with given the specific value E for the evidence variable E. So we have the query variables which are represented as Y, and then we have the evidence variable represented as E. And let's suppose there are hidden variables as well, and that is represented by H is equal to X minus Y minus E. So X is actually all the variables we have. So we minus the query variables and minus the evidence variable, we can get out the hidden variables. Then the required summation of joint entries is done by summing out the hidden variable. So if you want to require the sum of all joint entries, then you sum out the hidden variables. So P, Y given E, given evidence. So probability of a query variable given the evidence E is equal to alpha P query variable, the evidence E is equal to alpha sum of all H P where given variable query variable Y with given evidence and the hidden variable. The terms in the summation are joined because Y, E and H together exhaust the set of random variables. So there you talked about various terms. So in the summation you have the terms are what are the joint entries because Y, E and H together exhaust the set of random variables. So you have the query variable, you have the evidence variable, and then you have uh, the hidden variable. So therefore you exhaust the set of random variable. So there are various problems we have to deal with if you use this method, that is inference by enumeration. So here the time complexity is much higher. So you can apply this method, but the problem is that here we have the worst time complexity, and that is big O d raised to the power n, where d is the largest arity. Space complexity is again d raised to the power n to store the joint distribution. So we have to have all those values of random variable have to be kept. So we need the space complexity, which is similar to the time complexity. So how to find the numbers for big O, G, N entries? So how we can look into it, how we can find those values. So therefore, we talk about here the concept of independence. What is meant by an independence? Definition, if you see this definition, which says that A and B are independent if and only if, this IFFF says if and only if, when this is possible. When A and B are independent, when probability of A given B is equal to probability of A, it means it is independent. Or the probability of B given A is same as probability of B, it means it is independent. Or probability of A comma B is equal to probability of A multiplied by probability of B. If these scenarios are there, then it is clear that A and B are independent. So let's see in this diagram, and you can see over here that we have the values cavity, tooth edge, weather, and catch. And let's suppose we decomposes into cavity, tooth edge, and catch, and we separate the weather, because if we talk about probability of tooth edge, catch, cavity, and weather is equal to probability of tooth edge, catch, cavity multiplied by the properties of weather. So here we have 32 entries actually reduced to 12, because all other entries are not possible. So if you have other combinations cannot be defined over here. So for n independent Bayes-Coin, you can say that 2 raised to the power n entries reduces to n. Absolute independence is very powerful but very rare. So obviously, whenever we are talking about various variables in the given particular domain, uh, you will not get the absolute independence. So we talk about various variables, but obviously that has some dependence. For example, if we are using it for a disease network or from a diagnostic problem, so there you go for various types of effects you have, and you relate those various effects together. But sometimes if you want to mix with the effects with whatever the mental situation which you are going through, or the characteristics of weather, if you want to include into it, or a climate, sometimes these are relevant, sometimes these are totally irrelevant. So it again, whenever we are talking about a particular domain in which we are actually looking for these independence, so we do not have any concept of absolute independence. So you cannot say that, okay, A has nothing to do with the B, or C or D, or B has nothing to do with the C or D. So actually we're talking about a particular domain. So obviously there is some sort of dependence. Okay. So dentistry is a large field with hundreds of variables, none of which are independent. So obviously there are so many variables which are related to dentistry. Here we are just taking only 2 to 3 variables. So we have to see, we have to look into the domain knowledge to find out what dependence they have. We have to interact with the experts in the field while we are making such systems, or we want to transform those systems. Conditional independence. We talked about independence. Now we talk about conditional independence. Let's suppose if P probability of tooth edge, comma, cavity catch. So there are 3 possibilities. So they have 2 raised to the power 3 minus 1 is equal to 7 independent entries. If I have a cavity, then the probability that the probe catches in it does not depend on whether I have a tooth edge. Nothing has to do. So probability of catch given tooth edge, comma, cavity is equal to probability of catch, comma, no probability of catch given the cavity. The same independence holds if I haven't got a cavity. So let's suppose I haven't had that cavity, then same rule applies. So here we have the same independence holds if I haven't got a cavity, yes, because it does not depend upon it. Catch is conditionally independent of tooth edge given cavity. It does not matter whether there is a catch or not. So that is why it is conditionally independent. So equivalent statement might be the probability of tooth edge given catch and the cavity is there. So that is equal to probability of tooth edge given the cavity. And the probability of tooth edge comma catch given the cavity is equivalent to probability of tooth edge given cavity multiplied by the probability of catch given cavity. So that is the concept of conditional independence. So there you have to find out all the independent entries and then you can see where you have that conditional independence. And again, by representing it with the same chain rule, which we have discussed earlier on. So we have to write the full joint probability distribution using the chain rule, where we have the probability of tooth edge, cavity, catch, and cavity. And here you can see that is equivalent to probability of tooth edge given catch, comma cavity, multiplied by probability of catch, comma cavity, probability of tooth edge given catch, comma cavity is the probability of catch given cavity multiplied by probability of cavity, so on and so forth. So it means there are 2 plus 2 plus 1 is equal to 5 independent numbers. Equations 1 and 2 remove 2. In most cases, the use of conditional independence reduces the size of the representation of the joint distribution from exponential in n linear to n linear in n. So if we apply that condition independence rule, then it works well for the problems and we can reduce the size of the problem. The size of representation is also reduced. So instead of including all those possibilities, we can only rely on those where we have that conditional independence. And conditional independence is our most basic and robust form of knowledge about uncertain environment. So that is the concept of a Bayes rule, which actually is the outcome of this lecture, that how you can apply that Bayes rule, the product rule, which is probability of A and B is equal to probability of A given B multiplied by probability of B, or it is equivalent to probability of B given A multiplied by probability of A. So Bayes rule can be defined further as probability of A given B is equal to probability of B given A multiplied by probability of A divided by probability of B. And if you want to represent in the form of the distribution, then you can take as capital Y, capital X as your random variable. So probability of Y given X is equal to probability of X given Y multiplied by probability of Y divided by probability of X, which is alpha probability of X given Y, Py, where alpha is what? Is a constant. Useful for assessing diagnostic probability from causal probability. So there are two approaches. Either we can go for diagnostic, you can say diagnostic probability, or either we can use for causal. So either we can use or infer cause from effects. Whenever I say I infer cause from effects, then it is a diagnostic one. And whenever it's a reverse, that infer effects from the cause, then it is called the causal. So obviously, when you have some causal probability with yourself, then it will help you to assess the diagnostic probability. So that is represented in terms of probability of cause given effect is equal to probability of effect given cause multiplied by probability of cause divided by probability of effect. So this is the representation in terms of diagnostic probability. So let, for example, here that let M be the meningitis and S is represent the stiff neck. And let's suppose the probability of meningitis is 1 upon 50,000 and the probability of S, let's suppose stiff neck is equal to 0.01 and the probability of S given M is, let's suppose, 0.7. So what is the probability of meningitis given that I have a stiff neck? So that it means that says that probability of M given S is equal to probability of S given M multiplied by probability of M divided by probability of S. And in this case, it will be 0.7 multiplied by 1 upon 50,000 divided by 0.01, which gives you the value 0.0014. The posterior probability of meningitis is still very, very small. You can see it is 0.0014. So in this way, you can compute the posterior probabilities of the given variable. So Bayes rule and conditional independence. So concept of Bayes rule with, if you apply that concept with the conditional independence, you can say the probability of cavity given tooth age and catch is equal to alpha, that is the constant probability of tooth age and catch given cavity multiplied by the probability of cavity, or it is also equal to probability or alpha probability of tooth age given cavity multiplied by probability of catch given cavity multiplied by probability of cavity. This is the example of a Bayes model. So we have the probability of cause given effect 1 give comma dot 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 giving effect n is equal to probability of cause product I p effect I given cause. So if you go for the parameters, you can find out it's a linear one where you can see in this diagram that where you have the cause and then you have various effects. For example, you have the cavity because of tooth age, you might have the cavity using catch. So the total number of parameters in this case is what? Is linear. So it basically is a linear progression. And let's apply this same concept in a Wumpus world scenario. So a Wumpus world scenario is also described in chapter number 3, or chapter number 7, which gives you the understanding of the concept where that Wumpus world agent, that agent has to proceed in 4 by 4 squares, and here Pij is what? Is true if and only if Ij contains a pit. So Pij represents a random variable, Pij, and when it is true, it's a Boolean one. When it will be true, when there is a pit, and Bij represents the breeze in the given Ij, and if it is true, it means that we have a breeze in that particular. So we include only B11, B12, B21 in the probability model. So let's assume that we just take B12, B11, which one, this one, B12, which is this one, and B21, which is this one. So here we only take all these three. The full joint distribution is probability of P11, comma that dot 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 P44, comma B11, B12, B21. So here we are talking about the probability of pits with reference to the breeze we have, because in the Wumpus world scenario, we have a relationship in the Wumpus world, and that relationship of pit and breeze is that pit cause breeze in the adjacent square. So remember that condition. So apply product rule. So if you apply the product rule, so probability of B11, comma B12, comma B21 given the pits at 11 till P44 multiplied by the probability of P11 to P44. First term 1 if pits are adjacent to breeze, 0 otherwise. Second term, pits are placed randomly, probability 0.2 per square. When it will be 1, it will be 1 when it is adjacent to breeze. Why? Because there is a condition that pit calls breeze in the adjacent square. And second is, let's suppose we arrange those pits randomly and we don't know where is it exactly right now. So that probability is what? That probability is 0.2 per square. So here, if you calculate this Pij, that will be equal to 0.2 raised to the power n multiplied by 0.8 raised to the power 16 minus n for n number of pits. So we know the following facts. What are the following facts? There is no breeze in 1, 1. There is a breeze in 1, 2, and there is a breeze in 2, 1. Let's see the model again. So let's suppose by considering this model, now we have certain facts with ourselves. What are those facts? That there is no breeze in 1, 1, and there is breeze in 1, 2, and there is breeze in 2, 1. And what is known to you? That there is no pit in 1, 1, there is no pit in 2, 2, and there is no pit in 2, 1. So let's suppose what the query is, that probability of P1, 3 given known, B. Define unknown is equal to Pij's other than P13 and known. So you take the other value apart from that Pij. For inference by enumeration, we can say that P13 given known, B is equal to alpha, that is a constant. Sigma unknown, probability of P13, unknown, known, B grows exponentially with the number of squares. So as your number of square increases, obviously it will go exponentially because it will make comparison with each square which is there. Observations are conditionally independent of other hidden squares given neighboring hidden squares. These observations are what? Are conditionally independent of what? Of other hidden squares, which I don't know. Given neighboring hidden squares. So define unknown is equal to what? Fringe union others. So you can say the probability of B given P13 is known, unknown is equal to probability of B given probability of 13, known, fringe. Now we can manipulate the query into form where you can use this. Now we can manipulate the query into form where you can have various combinations of the known with the fringe and with the 13, and you can compute those values. And let's suppose these are the possibilities we have in that particular case where we know exactly as it is given in this diagram the situation which is given to us. So let's conclude the topic over here, and which is just give you a one page summary that probability is a rigorous formalism for uncertain knowledge, and we can have that formalism available to us where you can formulate the problems wherever you have that uncertainty. Joint probability distribution specifies the probability of every atomic event there we have. So how many atomic events are there? There are many atomic events which are possible. So you can have a joint probability distribution function. So queries can be answered by summing over atomic events. So if you add all events together, you can answer those queries. And for non-trivial domains, we must find a way to reduce the joint size. So if we are able to reduce the joint size, then we can also compute it. Independence and conditional independence provides the tool for that. So that is the concept which we have discussed about independence and conditional independence, and there that help us to reduce uh, our domain, and we can restrict to the possible number of combinations which can be formed. Um, so with this, I conclude over here. Thank you so much. And then our next lecture will be on the Bayesian networks and how we can use Bayesian learning to design a certain agent. Thank you so much.